Muchas gracias. Como anunciamos, vamos a dar la charla en inglés. So, good afternoon. Thank you all for coming. We are going to talk about a paper that explains how to build vector representation of programs, and we are trying to explain why and how are we going to convert code to essentially numbers. But first of all, a bit of introduction to put a bit of context of who we are and why we're especially interested in this topic. I'm Guillermo, he's Dami, and we're the data science team at SourceD. Essentially what we are doing at SourceD is trying a new approach to recruitment. So we are trying to find good job offers for developers based on code analysis. So that's our main focus. We are trying to analyze the code and match build a technical profile of the developers based on that code and do some matching with some jobs that might be interesting for them. So as you might guess, taking that into account, code analysis is pretty important for us. It's essentially the core of the reasoning that we have for contacting developers, and in order to do code analysis, we have to detect like the style, the structure of the code. So that's actually a feature extraction for those of you that are familiar with machine learning techniques. We are also interested in finding similarities between coders. So in translated to machine learning terms, that would be a clusterization problem. We are interested in pairing coders with job offers. So that would be essentially code-based filtering, content-based filtering, sorry. So essentially, in order to solve these problems, deep learning is, a very well-suited tool for these problems. We are going to explain why and some of the reasons behind that. Essentially, deep learning is, an evolution of machine learning, and at the end, it's essentially layers and layers of neural networks with many different architectures and adapted to the problem more or less. So a bit of what we're going to talk about this afternoon. We are going to start talking about vectorization. What exactly is vectorization? Why do we need it? In order to make it more clear why we need it and why and how we do it, we're going to cover an example with natural language, which is Word2Vec. It's well known, and it's more clear to explain than diving directly into source code. And then we'll move to the actual content of the paper that we're going to discuss, which is source code vectorization. In order to discuss source code vectorization, we need to understand, how code is different from natural language, why we need to pay attention to code structure, how we build vector representation for code units, the training algorithm that we use in order to come up with those vector representations, and after that, after we have built those vector representations, what's next, what we can do with that.
Okay, thank you. Okay, so first thing first, hello everyone, I'm Dani. First thing first, we need to get like a general idea of what deep learning does. Deep learning basically works like this. You put in a problem, magic happens, nobody understands it, really nobody understands it, and then you get a solution. Of course, deep learning is not so simple, it's much more like this. You put in a bunch of numbers, and then lots of matching happens, which nobody understands, and then you get another bunch of numbers. So in the end, you need to encode your problem with a vector, with a bunch of numbers, and encode your solution with another vector, another bunch of numbers. So yeah, I mean, this is a bit silly, but it's how it works. So to get that to work, we need to vectorize our input, because we cannot just put in anything we want. Code, the same as natural language, is text-based. So it's hard to process with this because we need to put in their numbers. So if we need to convert to vectors, we need to do steps for that. Why vectors? Not only for deep learning. Also, if we have vectors, we can apply distances like the Euclidean distance, cosine distance, and these operations should be meaningful. Should give us a semantic relationship between between the elements that are represented by these vectors. It's easier to manipulate. You can move them to different spaces. There's a lot of things you can do. In the end, it's algebra there. If once you get algebra in there in the equation, once you get algebra in there, you can do lots of things because you're using like the power of maths to manipulate things that in the beginning were only text and you didn't really know what to do with them with enough power. So what is the problem of translating code to vectors? Well, it's actually the same problem at the root of transforming words to vectors, which we'll see later. The problem is that we can't just say, okay, so this word or this token of code is going to get this random vector, this another one, this another random vector, because this way we will not keep semantics. If we take the distance between two vectors, we're only going to see a random distance. We are not going to we are not going to compare them in any meaningful way, and any manipulation we do is also going to be meaningless because they are just random numbers. So how? And this is like the root of this talk, is how do we get code and transform it into vectors that we can later feed to the neural network, deep learning, magic, unicorn thing, and get out meaningful solutions or meaningful insights, or in our case, meaningful relationships between coders and code and companies and all these things. So this is a very well-known example. Some of you, I don't know if you have heard of it. It's done by Google. Basically, what they did, I'm going to explain it because it's easier to see this like in the world of words, and then we'll move to code. This is like just a transition, a very short explanation. So yeah, this is work by Google. What they did was, we want to find vector representations for words. The word dog, the word Spain, the word, I don't know, moon. And we want to keep these semantic relationships I was talking before just a minute ago. So what they did was, they took a huge collection of text. They did very smart things with that to extract them. I am not going to go into that because I mean that's a whole full talk. Very interesting too. And then, for example, they are using, well, one of the things they have used to show the success is showing distances between words, or showing how the relationship between the vectors actually reflect the semantics of words. So I'll give just a bit of examples. They are using here the cosine distance, okay, and it shows the similarity. So for example, in this one, is this a pointer? Oh, cool. In this one, they measured the distance to the vector for France. So and these are like the nearest words. If you made this list much longer with words that were farther, you would go farther and farther with words that would be semantically much more distant. If you take the distance between France and, I know we're going to say omelette, but maybe that's not so far. But if you say, sorry? Croissant, yeah, it will probably be nearer. I don't know. I would like to try that. And if you, I don't know, if you make France and the American Independence Day, maybe then you would be farther. Sorry. More examples. This is principal component analysis. It's just a technique to move multidimensional vectors into a two-dimensional representation. In the end, it's just a way to show things in a two-dimensional space that intuitively can relate to us as humans. So here, for example, you have countries and capitals, and the distance between countries and capitals is more or less consistent in this principal component analysis representation. That was hard to say. And well, yeah, I mean, there's nothing much that I can say that you are not seeing. This is very visual, and this represents part of the success of the word-to-vec algorithm, because this comes from the algorithm, and this is completely blind. It was only fed with pure text. So you get these relationships between Greece and Athens, Italy and Rome, and then the order here is the same that the order here. And this came up, I mean, these have not been sorted by a human afterward. This is what comes out if you do the PCA and project them into 2 dimensions. So, I mean, I think it's remarkable. And another last example. This is the same, another principal component analysis, and you see that car and bike are much closer, thank you, much closer than king and queen, which are closer between themselves. Then book and magazine, they are kind of close but not that much, so these things kind of hold when you create the vectors. So this is just an example. This is what Google did with words. So now we are aiming to do something similar with code. But code is not language. They have very deep differences that make it so if you just take the word2vec algorithm and just feed it a whole code base of your, I don't know, JavaScript code, it's not going to work properly because code and natural language have very fundamental differences. Some of them, which are easy to see. Natural language has a complex syntax, and we sometimes bend the syntax for expressiveness or whatever. Code has a much more simple syntax, but at the same time much more stricter. Vocabulary in language is much bigger than in code. In code you have like, I don't know, maybe 20 reserved words, 50, I don't know, 100 if you are doing C++, I don't know, but it's still very limited. And also related to that, in natural language, words that are similar are usually related. There are word roots. So the word double and the word doubles are the same word. And in code, that might not be the same because one might be a type and another one might be the name of a list of doubles. And then they are very, if you look at the morphology, they are very similar, but in the end, that similarity is not true because they have very different functions inside the code. So in the end, the semantics of code come from structural relations. I'm going to explain this because this is a bit, this is more related to this. In natural language, usually words that are together have some semantic relations because they are together in a sentence. You are talking, and the words that come together are usually semantically related. In code, the relation is not so obvious. Because when we look at code, we are looking at the structure. So this if contains this other thing, which contains this other thing. And the relations are more structural, are between things that might be farther away, but the relation they have in code is the important relation. We don't care that this thing is inside next to the if. Maybe this condition is related to another thing, which is, I think it's an intuitive concept, but I think if you all code, and I guess so, I don't know, but if you all code, I think you can relate to that. I don't know if I can put it better. In the end, it's a matter of more freedom versus more constraints, and yeah, that's like a good summary of that. So the end problem is that you just cannot use the same techniques you used in word2vec, which use locality of positions, use similar words by root, assumes a very rich vocabulary, assumes a complex syntax, so you have to throw that out the window because it's not going to work, and use a completely different technique. And now I'll give my...
Okay, so far we have more or less introduced the problem that we are trying to solve. We have made an analogy to natural language, but this would amount to cover more or less what is the state of the art of the paper. But we have come here to talk about like program vector representations, which is where the interesting part begins. To put a bit of context, essentially, we are going to discuss this paper. It's building vector programs representation for deep learning. It covers only like building the vector representations, not what to do with those representations. That's covered in this other paper. Essentially, all this has been done by this guy, Lily Mo, which is a PhD candidate from the Peking University. They are working in many, they are working mainly in ways to analyze the code. They are focusing more on analyzing code in order to detect plagiarism, in order to detect authorship of the code, but it might be useful for what we are trying to solve. Okay, so that was a bit like, okay, we haven't come here to hablar de nuestro libro. We have come here to talk about another paper from a guy, just to give a bit of context. So if we talk about how we do this and how we have done this, it's actually this guy. We are implementing this. We are very attached to it at the moment, but it's not our book at the end. So a bit of what Danny was mentioned before. We were mentioning that word roots, positional relations are something really important in natural language. As you can see here, it's really hard to tell anything by looking at the roots of this, and this. And at the end, these are many different things. Also, if you look at the positional aspect, the fact that this comes after this doesn't tell you much. This could be like follow, but it doesn't give you any meaning. What gives any meaning to this sentence, it's actually the syntactic structure. And that syntactic structure can be expressed as an abstract syntax tree. At the end, what you do is you parse this and you gather these different components, and yeah, that's it. But it's not like the actual words that contain most of the semantics about these lines of code. So we are dealing with a different kind of problem, definitely. So what we need to capture is, code has very specific properties, as we discussed. At the end, we can infer a lot about the semantics of the structure. There is like a parent-children relationship in these trees. You have this is a tree, there are leaves, children, etc. So we have to look at this relationship in order to understand the code and to gather some meaning out of it. And code has this, it's compositional. It's made of trees, and you can take one tree and put it under another and compose different levels of significance by combining different elements into a hierarchy. So at the end, we are looking for a vector representation that, for each node type, for instance, for the vec type function declaration, we need a unique vector that represents all the function declarations. The children, as I was saying before, all the children contribute to the actual meaning of this function declaration. So we need to find a way to generalize the function declaration that takes into account the children that are below all the function declarations. And we need to keep like semantics at the end into our vector representation. Okay, so that's enough talk. Let's go to a formula. That's the basic approach that we use for actually generalizing. For what we are trying to do here is build an approximation of a vector p, which in this case would be, For instance, we are trying to approximate the vector p, which would be the one at the top, by aggregating the vectors that are below the children. If you are familiar with, if you actually remember, like your artificial intelligence classes for college, this is pretty similar to the activation function of our neural networks. You have an hyperbolic tangent function, you have an input to your neuron, you have a weight that actually adjusts your input, and you have a bias term that you can use to adjust your function. So this is quite similar to actually a neural network, as we can see. The only difference with this is that we have this correction factor. With this correction factor, what we are trying to do is, apart from the weight that we are using in order to correct the signal, we are trying to adjust the importance of children depending of the number of leaves that this children has under, with relation to the total number of leaves that this vector has. So it's essentially another way to adjust the weight. The only thing is that this is deterministic, the L factor, and this is something that we can train into our algorithm process. So we will train for the weight and for the bias, as we will see later. So at the end, what we are trying to do is essentially we are trying to approximate a function, our function itself. And what our function does is build an approximation of the vector for n1 based on the different vectors, on the different children vectors. This is one example for training, and suppose that we have another vector of type n1, which would be the same type as we are dealing here. But in this case, this is another sample. This would be, for instance, a function definition. This would be a function definition as well, but these have different children under. What we are trying to find is this function that, given this and this, give us like a vector representation. So in order to do that, we need to describe the training process.
The training. Okay, so as Guillermo said, we have this function. We need to approximate. We need to find that function. It's never going to be perfect, because I mean, if it works for this and needs to work for this with the same W and B, if you remember, it's not going to be perfect. So we just need to get to the best approximation we can. Keep in mind that in the end, our end goal is finding the function, because we want to find the values of the vector representations of all our types of nodes. So this is, I mean, we are like wiggling at the same time the vectors and the matrix W and the matrix B, all at the same time, trying to find a way so that everything like kind of falls in place. And the vectors just work, because if we have the best vectors, then it means that the difference between the representation of a vector, of a parent, and its approximation with its children should be as small as possible. Yeah, I mean, I don't have anything to add to that. I can say it again if it was not clear. In the end, you're trying to find these mythical vector representations, and you need them. So you try to figure out at the same time what is this W, what is this B, and what is this vector of things, and make them all fit together and make this as small as possible. This is just the square of the Euclidean whatever. I had to look it up. That's why I say it, because maybe someone isn't familiar, so I didn't know it the first time I saw it. But okay, this is just a distance, a very simple distance. So
the cosine distance, right?
I think this is Euclidean distance. I think.
Notation is for Euclidean.
This is for Euclidean. I mean, yes. I mean, we took the paper. We believed our friend Lily Mo, and we decided that we were going to follow his steps. He used a Euclidean distance, so that's what we are trying. We could try a different one at this point, I think, because that's. Fortunately, that was one not of the hard parts to get right. Okay, so but this thing, it has a maybe not so subtle problem, and it has a trivial solution. I just write 0, 0, 0, 0, 0, the distance is minimum, okay, we're done, finish. Of course, that's not what we want, because it's not very useful. So what do? We do what is called negative sampling. it has a weird name, but in the end it's just, okay, so I have this sample of this node with its children. Let's just replace either the root node or one of its children by some random thing, and then this will be not valid code. It will be an invalid tree. And if we have an invalid tree that represents invalid code, then this represents the invalid one, this is the valid one, which we took from our code base, which we are using for training, because we are training on a real code base. Maybe I didn't say that, but of course we do. So the difference between them should at least be a number, delta here, which is usually 1. It's a bit arbitrary. And then you put the max, because once you have this difference, you don't need to get it further. So in the end, what you're trying to do is, if I take this bunch of examples of code and then make a negative sample for all of them by replacing random parts of it, and then I aggregate the sums of the difference all together, well, before aggregating, and then compare the difference, we should get as near to 0 as possible. Because that will be the thing that we'll be minimizing. We actually minimize the sum of all of them and then regularization, blah, 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 blah. But in the end, what you want to minimize is that thing. If this gets to 0, it means that the negative is obviously bad enough to get a bigger distance. So then our distances are meaningful, because when we add a modified one, we are getting a distance which is always bigger. I don't know if this makes sense, if I made a mess when I was trying to... I mean, this is like the real trick of the whole thing. You just randomly change one, and that must have a bigger distance. So if we try to minimize this, we are going to get get that distance, those meaningful vectors. Sorry. How do we do this? This is a gradient descent. If you've done any machine learning or anything, I mean, I'm not going to go into depth with this, because this is like a very well-known algorithm. You just feed it a function, tell it to iterate with different set of examples. It starts like going down a valley, multi-dimensional valley. I wanted to say that. And well, with examples and time and processing power, you make it smaller. So that's how you do the training, and how you this thing we were saying at the beginning, like trying to make everything fit together, the vectors and the W's and the B's and everything. This is how you get them to fit, by forcing that function to get smaller. And I think I've talked too much already, so it's time for Guillermo.
Okay, so after we have gone through this training process, which takes hours, days in some cases, we need to evaluate what have we gotten out of it. What we have been doing all along the process is essentially unsupervised learning, which means that it's painful. It's painful to train, because you have to find ways to make up for your lack of examples, such as was the training function that we were trying to minimize. And it's painful because you have to find a way to validate your results. Happily, in this case, it's relatively straightforward to validate your results. What has been done in the paper essentially is the guy has tried to take the vectors that come out of the training process and make clusters out of them, make groups. So the first clustering implementation that has been presented in the paper is its nearest neighbors. So essentially you try to find what are your most similar, the closest vectors in your vicinity. And we can see some meaningful results already. You can see that the vector for ID and the vector for constants, which are the ones that deal with data representation, with data to reference are pretty close to each other in both sense. Constancy is the closest to ID and the other way around. You can see as well that the vectors that deal with loops and with essentially control flow, if it's closer to for it's closer to if, break is closer to while it's closer to switch, and while to continue. And finally, also data manipulation. Write reference and binary op are also pretty close to each other. So it seems like the vector representations that we get at the end of the training steps make sense from this point of view. But he has tried also another way to validate the results to analyze what we have gotten out of it. Essentially, k-means what tries to obtain, it's, okay, let's try to build 3 different types without knowing a priori the types. So it's trying to infer some types. So in this case, each cluster would be equivalent to a certain type. On this one, you can see that these operations are mainly about data reference, manipulation, again, by ID, constant, manipulation, binary operations. So it's more a type that more or less makes sense. As for the second type, it's mainly about declaration. You have a function definition, you have a type declaration, array declaration, etc. And finally, the third one, it's, okay, this is a bit less clear, more complex, but you can see that most of the ones that have to do with control flow, again, are here, while, if, go to. So the results more or less make sense. So we can consider that the vectors, the actual representations that we have gotten for these different types of operations make sense at the end of our training process, right?
Yeah. So, okay, so after that, what can we come up with? Because right now, what we have, if we get this to work, the whole algorithm, the training, blah blah blah, you get representations for tokens. I mean, all these things are tokens, but every if in the code is going to get the same vector representation. Every while in the code is going to get the same vector representation. That's something, but that's not good enough if you want to do some kind of code analysis as a whole, as in what is the style of this function, what is the structure, what is this module, what is the complexity, whatever. We don't even know what we want to struct there. But if you want to struct something, you need to combine those into another vector, because you will need to feed another algorithm, another machine learning algorithm, deep learning, whatever. You need vectors for code structures. So you need to move from tokens to structures. So if, for example, if we had this very simple tree, and for each one of these, the declaration has this vector, which is always the same for each declaration. This binary op has this one. So there should be a way to take all this and make them into a different vector representation to feed it to some other neural network or whatever. And this way, when we manipulate this, we are manipulating this, and we can make assumptions. No, we can extract information from a higher level of abstraction. And that's kind of a teaser trailer, because we are not going to explain the next one. It's in the second paper. It's very interesting too, but I mean, we don't want to be talking here for 2 hours straight. So, and you don't want to be listening to us for 2 hours straight. So yeah. Sorry. But if we get there, where are the applications? I was already talking about them. We can start if we get there, and the paper is there, and we are going to implement it, and we'll see if it works as well as it promises. If we get there, what we want to do is things like find similarities in the structure of the code, identify some kind of style. Style can be many things. Can be this person writes very long functions and this person doesn't. If you include comments in the abstract syntax tree, which is not so weird, you could get does this person document a lot or not, or these kind of things that we intuitively do when we look at code and we compare the styles, and maybe you even look at your coworker's code and say, you did this, I know that. If we could do that automatically, well, I mean, it's mind-blowing. We wish to get there. we're doing our small steps. So yeah, basically what we want to do is do this kind of matching based on semantic information about the code, stylistic, structural, these kind of things that we as humans do. Can we teach a machine how to do that? Well, for that we need the representation of at least functions or chunks of code or whatever. And yeah, well, in the end for us it's improving our matching. This is momento publicidad. But yeah, that are the applications that we are working on and that are very interesting to us. And I think after this, it seems clear that this could be a way to attack those problems. And I think, yeah, no?
Yeah, we're done.
Oh, we're done? Ah, good. Oh, it said next slide, Guillermo, and I thought you had. So, questions, comments, here, our contact is there. Yeah?
How does this compare with traditional code complexity metrics? So, for example, I see that this sort of technique might be language agnostic. So you can run the same code, the same neural network processing over any single programming language. But have you done a comparison test over, Micra complexity and this sort of metrics to define similarities?
Okay, so just for the micro, I'm going to repeat the question. Sorry, but because maybe I didn't get it. If I understand you properly, is if we have compared it with methods that use code complexity and other kind of metrics to do this kind of comparisons. And did I understand you properly?
Yeah.
Okay, so we did not do it personally, but correct me if I'm wrong. I think that in the paper he was comparing the results with other techniques and he was getting better results. In the paper we did not explain it because it had like a long list of results. One of the results he had, he was training with, there was like a set of 8 problems that were solved by students, and then he got the solutions, and then he was trying to match each solution to each piece of code, and each piece of code to each problem, because it was solving that. So this code solves problem number 7 or whatever. And if I remember correctly, it was working better. We have not, we believed him. We have not gone any deeper into that. So maybe there's something we have missed. I don't know, but we were expecting this to get better because we believed the paper. Is this? I don't know if.
Just out of curiosity.
No, yeah. It's a very good question, but we assumed that if the results were more promising, we were trying this route.
I have one question and 2 or 3 suggestions. The question is, you said. The comments put it in the AST, that's breaking my head. The lecture takes out so how do you?
Well, the question is, once again, what about the comments in the AST? It depends. For example, in Go, if you read the AST with the AST Go parser, it gives you the comments because they are meaningful. It gives you the comments. If you do it in Python, they come as doc strings which are attached to the corresponding object which has and I don't know. I'm pretty sure that in languages where kind of doc strings are a thing, it's probably in there. And if it's not, maybe in the language parser, because it's done. Maybe I'm really sure that C doesn't do it. But maybe there's another parser that is used by a code indenter or something that does it because it needs to manipulate it. So you can always, if it's not in the original language, you should always be able to.
So an annotated tree.
Yeah, it's like an annotated tree. Yeah, it all depends on if you consider that comments are part of the code or not, which is like very philosophical. We can talk about that with beers later. But yes, I mean, if you don't have them, we will have to work with other things. But some languages we have looked into, they have it. So we have there. There was another question.
Now the suggestions.
Oh, okay. Sorry.
So one thing, I've tried a lot of things and tried myself to write stuff for detecting plagiarism. And I think your problem is slightly different, and you're losing information by losing the identifiers chosen by the programmer. Well, I mean, when you're working on plagiarism, the identifiers, you have to consider them part of the attack. I don't know how to call it. So someone who is rewriting the code, one of the easiest transforms is to change the identifiers. Another is to make simple transformations in the code, so you have transformations in the syntax tree which are sort of equivalent in some sense. And so, but in your case, because I don't think you're trying to detect plagiarism, you're trying to actually compare code. So if you think of just the identifiers and your friends, I think by the identifiers you chose, you can probably detect your friends somehow. Some people are more terrorists. I mean, there's information there. I'm not saying all the information is there, but there's information there. So in your example of the double and the double E or whatever, the problem there is one of the doubles is part of the syntax of the language. The other double is actually chosen by someone. And there's information there in the sense that double there means something in the natural language sort of. I mean, it's highly idiosyncratic, but there's stuff there.
One thing we have discussed, and we don't really know how we will approach it, but we need to approach it, is precisely that. We will probably not be able to do everything we want to do just with this. So in the end, you end up with kind of a hybrid system that does this, lexical analysis on one side, and then machine learning, deep learning, magic analysis on the other end, and then you somehow combine them or use one to inform the other.
Maybe you can have different components in the
or something. I don't know.
We're working on different levels of abstraction up to a certain point. We're working on the syntactic level here, and what you're saying is
sort of. I mean, if you think of the lecture hack, you're actually annotating the. I mean, it's sort of in the almost there.
Yeah, there's a lot more there. So, but yeah, that's a very good point.
Okay. Have you tried to find some patterns? I mean, good practices across languages, because I think it's quite complex to detect or rate. So, you have to hire a developer. It has skills for two languages, and they have to apply some common pattern between languages. The problem, I think, is that part of this analysis has to depend on the language.
Yep.
So, how to deal with that?
We are not there yet. We are not there yet. We are still trying to extract meaningful vectors, and I mean, we are re-implementing all of this in TensorFlow. So you can imagine TensorFlow came up in December, November? We haven't had much time. I mean, you are right. It's one of the things we really need to think about. It's a very good idea, but I mean, we are not there yet.
You think it's possible? I think because, I don't know, I might just focus on one language, okay, and one common pattern. How can you detect that there is a pattern? Because you can have several lines of code that doesn't make any sense for the pattern, but in fact it's a pattern.
One thing that comes to mind, for example, is if in one language we can detect that you're using the teachings of Uncle Bob by clean code, maybe we can do something to move that to another space. Maybe, I don't know, this is a crazy idea, don't quote me on this, but maybe it would be possible, because in the end you have like things that are very similar in languages, and you will have like to do a bridge in there. I mean, it's not crazy, but we are not there. We are not there.
Again, what we make is compare code from the company with the code of the people, so we don't need to define nothing. It's just see how far it is from the company.
Yeah, but what he says is across languages you cannot do it.
You have mentioned that one of the goals of the product is just matching developers with your offer.
Yeah.
Yeah, but we have the code from the company of the software.
Ah, okay.
So we compare the code of the company with the code of the developer.
Okay.
Yeah.
Okay. The whole goal.
And that would be in the same language, because now we are working with that restriction that it's the same language, because if not, it's like too hard for us.
It has its own vocabulary, different words, so it's not straightforward. And it's not straightforward to move all the languages to a common ground, to a common vocabulary. So that's something that.
Okay. Anything?
Can you go back to the slide with the distances calculation?
With the distances?
Yeah. The farther.
This?
No. The one you.
Ah, the formula.
Yeah, this is part.
This one?
Which parts do you compute, or does the system compute automatically? And which parts do you input as a scientist? In other words, which parts are your bias? Which things are you defining?
So the question is, which are our
The things that we train.
the things that we train for? So we train for the vector representations of everything. We train for this W thing and this bias thing.
So you define the initial vectors. That's the only
We find, sorry?
the initial vectors.
The initial vectors are random because you just need them to end up fitting. So if you have enough processing power and run this 10 times, you're going to get 10 different sets of vectors. But in the end, it's not important which are the actual numbers in there, because the important thing is the relationship between the vectors.